Instead of having to do the limit of the difference quotient every single time, we have what's called the power rule. Okay? If you have a to the x raised to the n power, its derivative becomes n times a x to the n minus 1. I'll let you write it down and we'll talk about it again. If your function is a times x to the n, the a stays there. It is a constant, okay? If you have a constant multiplied to your function, it stays along for the ride. Nothing happens to it. It stays with it. But what happens is since x is raised to the n power, that n power gets multiplied to your coefficient, and then the power decreases by 1. A pattern that about half of you picked up on at least a piece of. Okay. Looking up at the board, you can see how that has worked. Okay. I'm going to go up here to pod 4, x squared. 2 came down to be the coefficient, x is now to the first power. Okay. If we look at 4x, 4 is the coefficient, x to the first power becomes x to the 0 power. Okay. Basically, we just take the coefficient if it's x to the first power. Okay. X cubed. 3 is your n, x to the n minus 1, x to the second. Okay. Now, is every single function written like a x to the n? No. But there are some things that we can do to maybe rewrite a function to make it look like ax to the n power so that we can use the power rule. Okay, so let's look at a few examples of this put into action. So f of x is 2x cubed. Okay. Our derivative, the constant always stays, times, okay, our power is 3, it gets moved down, and then becomes 1 less. So 6x squared is the derivative of 2x cubed. That took us about 10 seconds. Yesterday, it would have taken us how long? Like 2 minutes. Okay? Doesn't that make you excited? It makes me excited. All right, g of x. You really would not have been happy if I gave this to you yesterday, right? No way. Tell me no way. Okay? But does this look like ax to the n? Could we rewrite it as ax to the n? Okay? We need to rewrite this as 1/3 x raised to the 1/3 power. Now it's in the form ax to the n, and we can go ahead and use the power rule. Okay? Those of you who know anybody who took calculus last year, at the end of the year we go to what's called Calculus the Musical. They have an entire song about the power rule because it is so wonderful. Okay. All right. So 1/3 is the constant that stays out in front. Our power is 1/3, so we bring down the power, and then we have to decrease our power by 1. What would our power become? negative 2/3. Okay? I will allow you to write this as 1/9 x to the negative 2/3, or you can write it as 1/9 x to the 2/3. You can write it as 1/9 cubed root of x squared. I really don't care how you write it as long as you get to a version of that. Okay. Currently, does this look like ax to the n? No. Okay, so let's rewrite it. We have 6x raised to the, if the 5th root of x cubed is in our denominator, how do we have to write the exponent for x? Negative 3/5. Negative because it's in the denominator. And then remember, whatever the root is would be the denominator of our exponent. Awesome. So the derivative. Okay. 6 stays along for the ride. Our power is negative 3/5, so we bring down the power and we decrease our power by 1. So our power becomes negative 8/5. We have to subtract 1, so 5/5, right? So negative 18/5 x to the negative 8/5. And I am perfectly happy with you leaving it like that or rewriting it if you want. I don't really care. Okay. Now there's a couple of things that I have been saying or doing up here that we haven't like really officially talked about. Like I keep talking about this constant staying along for the ride. And like over here, we looked at derivative of two terms together. Okay, so let's just officially make these rules known. All right. If we have the sum or difference of two functions, when we take their derivatives, we can take their derivatives separately and still keep the addition or subtraction. That's essentially what we were doing with the x squared plus 4x. We take the derivative of x squared plus we take the derivative of 4x. Okay? So if you need to write that down. Okay. It's something that kind of just comes natural, but we have to make sure that we are following the rules, okay? And it is a rule. It's just something that we kind of, I like to kind of, I don't know. I guess I forget it's a rule, it just like becomes second nature, right? And then that constant that I keep talking about, if we have a constant multiplied to a function, that constant still gets multiplied to the derivative. Okay, so I like to say it stays along for the ride. Okay, it's stuck there. This is like the first year that nobody has made a comment. Yes.
Why is constant spelled?
Why is constant spelled with a K? So that you pay attention to it. Okay, we like to use K for a constant in calculus as far as when we're talking about derivatives. And so I found a graphic that had it spelled as a K, and I just thought it was attention grabbing. How's that? No other purpose. That is not how you spell a word. Okay? All right, 2 additional rules that I would like you to remember. The derivative of sine is cosine, and the derivative of cosine is negative sine. We kind of talked about yesterday how they were probably going to be related to each other. Well, here is the official relation between function and derivative. Now, I won't do this often, but I'll do it more often than I did last year. There are times where it is beneficial for you to see why rules are the way that they are, okay? So there will be some times where I prove some things to you, okay? Some of you are going to be pursuing careers in mathematics, and if that is the case, then you will be doing a lot of mathematical proofs. So sometimes I think it is good for you to be exposed to that. Okay, so I want to go through why the sine rule is what it is. Okay, why is the derivative of sine cosine? All right, so let's work with what we know. We know that the derivative of sine with respect to x would be the limit as h approaches 0 of sine of x plus h minus sine of x all over h. Okay. Now, you are not going to remember this off the top of your head, but last year in pre-calculus, you did work with some trig identities that involved addition inside sine, cosine, and tangent. Can you at least somewhat recall doing that? Okay, you're probably not going to remember the identity. Maybe someone does. I don't know. I won't say that nobody does. But a majority of us, I don't think this is even one I made you remember. I think I gave you a note card for it. Or I didn't give you guys note cards. It was on your test, right? So if we use the sine sum formula, we can rewrite it as sine x times cosine h plus cosine x sine h. Okay, so I just rewrote sine of x plus h to this. All right, how could that be helpful? Okay, we don't have anything in common altogether, do we? No, we do not. Okay, but we have two terms that have a sine x in common. Do you agree? All right, so this is what I'm going to do. I'm going to rearrange this to where sine of x cosine of h is grouped with sine of x. And then I'm going to separate cosine of x sine of h. Bye, everyone. Okay. So I rearranged and separated into two fractions. Okay. From here, we all can solve this together. What can I do with this first fraction right here? Factor out a sine of x. Okay. We know some special limits. As h approaches 0, what happens to cosine of h minus 1 over h? Okay. What happens to sine of h over h? Okay. So sine times 0, 0, we're left with this one. Thank you, Trevor. you replicate that? No, but it's good for you to know that it is a rule for a reason, okay? So I have a couple more examples intermixed, and then I want to give you some time to start your homework, okay? Write this one down. What? Okay, this is one that people look at and they, oh my gosh, I don't know how to do that. Okay, but we have a lot of algebra skills where we can rewrite this. Okay, would you believe me when I say that every term could be written as ax to the n? Okay, good. I'm glad you believe me. All right. So that denominator, before we do anything else, how should we rewrite that denominator? What do you say, Trevor?
2x.
Okay. So then, if we were to rewrite it, 2x cubed divided by 2x to the 1/2 power would become what?
2x.
So you're trying to say 2.5, right? Okay, so 2 divided by 2 cancels. And then when we subtract the exponent, we're left with 2.5, which I'm going to write as 5/2. All right? Next term, we would have 3/2, negative 3/2, x to the okay. There's a lot of silence, so let's talk about why it's 3/2. We have x squared divided by x to the 1/2 for subtracting powers. 2 minus 1/2 would be 1.5. We need to write it as 3/2. Okay? Plus 7 divided by 2, x divided by x to the 1/2 would leave us with x to the 1/2. And then we have 5 divided by 2, x to the negative 1/2. If you are not the biggest fan of dividing by with exponents, then you could create that to be multiplied by x to the negative 1/2 if your brain works better with that. Okay, you have the capability of doing either one. So now this doesn't look so bad, right? So now dy dx. Okay, a little different notation for you there. Since there's y, you would either write y prime or dy dx, whichever one. Okay, power rule. 5/2 x to the 3/2 minus, when we apply the power rule, Chris, what would our coefficient turn into? 9/4. And then our power becomes 1/2 plus. Okay. When we take the derivative of 7/2 x to the 1/2, 1/2 multiplies down, so our coefficient is now 7/4 x to the negative 1/2. Very good. And then when we take this derivative, negative 1/2 multiplies out in front, so we have negative 5/4, and when we subtract 1, we're left with negative 3/2. Okay. Now, yeah, there's probably a way for us to get this answer to look in the same format of y, but that's not worth our time. All we need is this right here, and you can stop. Don't even rewrite it. Just leave it as that. Okay. Now, if we need to evaluate that derivative at a specific x value, then you may need to do some rewriting with those last two terms, but until then, you can just leave it the way that it is. Write this down and individually find the derivative. When you think you have the derivative, please check it with your neighbor. What? Amy, what's your derivative? Okay, let's do one term at a time. X to the first power would be this, right? X to the first power. So if we apply the power rule to that, it would just be 1. Very good. Okay? And then what did we talk about? What is the derivative of cosine? I'll let you look again. You back where you wrote it down.
I just have this cosine sine of x.
We'll come back to this right here. The derivative of cosine is negative sine x. Make sure you have that like high. Okay, there we go. That is why. Okay, very important. Can you not?
No, I didn't see it either. I didn't know it was there.
Okay, that is good to know. Thank you. Make sure you have negative sign for the derivative of cosine. Thank you, Amy. Yep. So I would like to see 1 minus sine of x as your answer. All right, one more example. So we might not have as much time as I had originally thought, but we've been having some good conversations, so that is okay. Go ahead and write down this example. Really big. Okay, I have confidence that you all are going to be very good at the power rule by the end of this homework assignment. However, where we get into trouble is when we need to rewrite, or when to know when to rewrite. Does this look like a x to the n? No. So we cannot use the power rule until we have terms that look like a x to the n. So what are we going to have to do? Huh? Okay. First, I would worry about that 3x plus 2, the quantity squared. That would get us 9x squared plus 12x plus 4. Then we could write 9x cubed plus 12x squared plus 4x to distribute the x through. And now we have 3 terms that look like a x to the n. Okay. Now we can find our derivative by using the power rule. Okay. So Joe, derivative of 9x cubed, what would you tell me?
18 squared.
Great. Plus the derivative of 12x squared, CJ.
24.
Good. Plus the derivative, yes.
Would it be 27x?
Joe, Do you agree with their, okay,
I accidentally redeployed my tweets.
okay, that's okay. Things like that happen, right? The derivative of 4x, Marcus.
4.
Yes. Say it with confidence. 4. Yeah. When it's x to the first power, we just look at that constant. Okay? All right, and there you have it. Okay? Now, like I said, problems like this right here that I'm underlining in green, I'm really not worried about those. But problems like this and this, you need to practice the rewriting and then applying the power rule. Because eventually we're going to get all these rules together that we're going to have to keep straight of when we can use what. Okay? So your homework you can find on page page 114. Okay? I did not receive everybody's graph match. So if you have not physically handed it to me, or you did not email it to me, you better do that. It will be considered late, but late is better than 0. Okay? Those of you who were able to do it, how long did it take you? 30 seconds, 20 seconds, 1 minute. That's what I'm hearing. Raise your hand if you did it multiple times. Okay? It's kind of fun, right? I think it's fun. But then again, like I teach